Thanks for the introduction, Chris. So yeah, let me start with a actual story. So my lab mate, whose name is Tang Yang, who lent his laptop to a friend. And what his friend does is very normal things. So he searched something on the web, and what the thing he searched is called Jeopardy! It's a TV show. And then there are some search results shows out, and things go very smoothly. However, this is not the end of story, and this Jeopardy! Show actually going to some further things. So they will be generate categories called I Love Jeopardy!, which is the recommendation engine actually inferred from the search of the Jeopardy!. And then it will go to the recommendation engine of this Google's recommendation engine, and then it's going to generate some more things in my friend Tang Yang's mobile phone. So what he received is he received something related to Jeopardy! Show on his Google Now, and he'll receive more shows like Let's Make a Deal and other things. However, my friend Tang Yang is not interested in this Jeopardy! Show at all. So he don't want his show on his cell phone, and therefore he wants this Jeopardy! Show to be deleted from his Google search history. So what he do is he just delete the Jeopardy! From the Google search. So he black out this search result. However, that he still receive a lot of those recommendations on his cell phone. The reason is because it's not just the data, which is the Jeopardy! Show, it is also the lineage, which is the recommendation engine and also the search result. And this is even amplified in the world of big data. So in the world of big data, you have some original data, and this data is going to generate more data. For example, a full-size image are going to generate a thumbnail, and a recommendation of those movies are going to generate more movies. And also, this data actually propagated through different clouds, and they're going to generate additional more data. And in such a world of big data, if we want to forget something, we want to forget it completely, both the data and the data lineage. So this is actually the first reason we want the system to forget, that is because there are some usability issues in this system. Next, I'm going to present a second reason that we want the system to forget. Say instead of search a Jeopardy! Show, this guy actually search a heart disease because that he has heart disease. And then with recommendation engine are going to recommend more medicines related to heart disease. Naturally, this guy don't want people to know that he has heart disease, and therefore he wants the system to forget that the fact that he has heart disease. However, as shown by previous paper, that it's not just the training data, but it also the recommendation engine, and people can actually infer that the guy have a heart disease from the recommendation engine, from the item matrix. And this is called system inference attack. So that's why when we want to delete the data, we also want to delete the original data and also the data lineage, which is recommendation engine and the search result. So this is the second reason we want the system to forget. Then we come to a third reason, that say that this is a system that tries to detect spam and benign email. So this works very perfectly. You have some person label spam or benign email, then we are going to label incoming samples as either benign or spam. However, according to adversary machine learning, that some people can actually pollute the training data. Say we have a bad ninja and who actually polluted the data, and therefore he can influence the detection result of existing spam detection engine, and a spam may be mislabeled as a benign email. And therefore, when we want to delete the data, which actually not just the original data, which is the polluted data, but also the data lineage, which is the polluted model and the result. So realizing this, what we are going to do is we come in for envision, which is called forgetting system. And such systems are capable of forgetting the particular data, which is, for example, is a rating for different movies, and also the data lineage, which could be some statistic of the data or the machine learning model, and everything be embedded in the cloud. So that means we're going to completely remove everything from the cloud. So this is our big envision, and the focus of the paper is we focus on machine learning engine. And therefore, this forgetting in machine learning engine is called machine unlearning, or for short, machine unlearning. And the ultimate way of doing unlearn is actually called retraining. So that's very simple. You just remove data to forget from the training data and retrain the engine from scratch. However, this could be very slow. For example, for a large data set, some of the training could take days to complete. And therefore, that's why we are going to talk about something called machine unlearning. There are two very important goals in this unlearning process, which are completeness and timeliness. Completeness means that how different this unlearned model is different from this retrained model. We want it to be as close as possible to the retrained model. And second is timelessness, means that how fast we're going to achieve the unlearning process. We want to shrink the vulnerable window as short as possible. The reason is because if it is longer, it's going to produce incorrect results as in the polluted model, or it's going to leak private information in the privacy motivations. So before I introduce the detail of machine learning, I first just introduce some background of existing machine learning model. So here is how existing machine learning model works. So we have some training data, and here the training data is x1, x2, x3, and x4. And then we're going to train a model based on the training data. And if we consider data dependency, this model actually depends on all the training data, which is x1, x2, x3, and x4. And now, let's take a look at the unlearn process. So in the unlearn process, what we're going to do is we transform the existing machine learning algorithm to a special form called status query learning. And such status query learning does is it changes the ground truth from each individual data to the statistic of the data. And inside here is the number of training data may be large, but the number of statistics is much less than the number of training data. And we show that many existing machine learning algorithms can be converted to the status query learning form with exactly the same precision. So we show in mathematical format that those two are exactly the same in the model. And examples are shown on the screen, which like naive Bayes, collaborative filtering, K-mean, SVM, and some other things. And now let's take a look at how statistical query learning works for the unlearning process. Now, still, we have all the training data, which is x1, x2, x3. And then, based on the training data, we're going to generate something called summation form. This shows one summation. So we first apply a function called G1 upon each of the training data, and then add them together. So the G1 will be very efficiently computed functions, such as like x1 square, x1 root square, or like x1 divided by the number of training data. So that is very efficiently computed functions. And then we have a limited number of summations. Based on different of the G functions, we can have G1 and G2, we can have some of those summations. And then we're going to compute this machine learning model purely on those summations instead of the initial training data. And then let's take a look at how this unlearn process works. So now assume that x4 is the data that we want to unlearn from this machine learning algorithm. So obviously, the first case is we remove it from the training data. So x4 is being deleted from the training data. And then what we're going to do is we're going to minus G1 x4 from the summation. So we'll update the summation. And then we'll also update other summations. After that, we're going to recompute the machine learning model based on the newly updated summations. And this is how the unlearn works in this statistical query learning. And this process is both complete and timely. For complete, the reason is because this process is exactly the same as if this data, which is x4, never existed before. So if you compute it just from x1 through x3, and the model is exactly the same, and that's why it's complete. And second, this process is also timely. The reason is because this process purely depends on the number of summations instead of the number of training data, and therefore the time complexity is based on number of summations. And the number of summation is much less than the number of training data, and that is why we are timely. So here I've introduced one of these status query learning, which we call non-adaptive status query learning. That's another type of status query learning, and we call it adaptive status query learning. So the difference is for non-adaptive status query learning, we know what the G function is. So we know the statistics up front. And for non-adaptive status query learning, we don't know these G functions up front. We need to decide the G functions based on previous result. And therefore, we need to go through different iterations until this function converge. So here is how it works. We have an initial state, which is S0, and then we're going to compute the next state, S1, based on the current state with S0, and it's the same summation form as I just introduced. And then we'll go through different iterations until this process converge. And say this example is after 10 iterations, and this process converge. And now let's take a look at the unlearning process in this adaptive status query learning. So what we're going to do is, for the last step, which is the iteration 10, what we're going to do is we're going to minus this G1, X9, Xk, which is the number, the data to forget, and we recompute the S10. And we're going to ask if this converge. Actually, in most of the case, it's already converged, and that's good, and we already finished our learning process. And if it doesn't converge, we need to go through its iterations again until it converges. It may go through 1 or 2 iterations until it converges. And as we show, this process is also mostly completed. If you are interested, please refer to our paper about the completeness. And also the process is also timely, and the reason is because that we start from the previous convergent point, and therefore this time complexity is much less than the time complexity start from the beginning. And after that, I'm going to introduce some case studies. So in the case study, we investigated 4 real-world systems, which are Landscape is an item recommendation engine, and it uses normalized cosine similarity as is training, as is a learning algorithm, and mostly it's like collaborative filtering. And Zozo, which is a JavaScript malware detection engine, and it uses naive Bayes and chi-square test as its detection engine. And the Go ETL, which is OS spam detection, and it uses decision tree as its detection engine. And the PGScan, which is a PDF malware detection engine, and it uses one class SVM as its learning algorithm. And also, we use some real-world data. For example, like a real-world JavaScript malware from Huawei and the real-world spams from online social networks. Now, let's take a look at the overall result. So what we're going to do is we're first going to perform real-world attacks on those 4 systems, which is those Landscape and Zozo stuff. And then we'll try to see if they are vulnerable to either privacy leaks, which is system inference attack, or vulnerable to pollution attacks. We show that Landscape is actually vulnerable to system inference attack, and all others are vulnerable to pollution attack. That means they all need unlearning if it gets polluted or leaking private information. And then we try to convert it to the summation form. And we show that all 3 of them, except for Go ETL's work, use decision tree, which cannot be converted to the summation form, but others can be smoothly converted to the summation form. And then we're going to show both analytical and empirical result. And from both analytically and empirically, that our unlearning process is faster than the retraining, which is magnitude larger than retraining. And also our process is complete if it can be converted to the summation form. Except for Go ETL, which is decision tree, it cannot be converted to the summation form. In conclusion, in this talk, we propose forgetting system, and in particular, this focus of the paper is on machine unlearning, which is to make machine learning engine forget they have learned before. And we convert existing system, in particular 4 real-world systems, to the summation form. And except for the Gao ETL, we have 3 of them. And we show that our unlearning is both complete, means that we can achieve the same result as retraining, and also we can achieve timeliness, which means we are fast enough. So now we come to the question, and it's a joke. So I would imagine that after the talk, that a question and answer. The question will be, what did this guy say in the unlearning talk? What's his name? I forgot. And I would expect the answer will be, I forgot. And that's actually our ultimate way of making system forget, is making a human being forget. Thank you.
Thanks very much, Inja. Does anyone have any questions?
Mm-hmm.
So thank you. I like very much the idea of unlearning.
Mm-hmm.
And you told us how you could do that for particular algorithms, but you didn't actually address the question of what about the lineage? If I'm in a cloud and I learn a model and I pass my model on to somebody else and that gets passed on, again, even though I retrain the first one, the old models are still floating around. So what do we do about that?
Yeah, thanks for the question. It's a great question. So actually, current version of the machine learning is just a prototype. So we only deal with lineage in the machine learning algorithm. So the machine learning model we call the lineage, and also the result, and that is the lineage we're currently talking about. We don't deal with other stuff. It's actually our future work. So we're envisioning a bigger system than just talking the machine learning talk.
Okay, great, thanks.
Thank you.
Interesting work. I have a question. It seems like in some of your discussions, you assume that you know which data you want to unlearn. But in some of the use cases, you may not know what happened. You know, for instance, in the case of your spam example, you don't know when the tampering of the data happened.
Yeah, that's a great question. So yeah, that's right. Like for some of them, we know, for example, like private data information, we know that the user specified which things to unlearn. For some of them, like spam, we don't know, but we say this kind of like orthogonal approach, so that like a more precise, for example, a human being is going to label all this data as like, okay, this is mislabeled data. And actually we have some huge future work in mind called adaptive called active machine learning. We try to probe which data to unlearn. So again, it's a great question. So currently it's just orthogonal and we haven't solved that yet. Yeah.
Okay,
Thanks.
thank you.
So I took a look at, you guys have a lot of evaluations of these real world systems. Do you have any impression for us of how much was work that you had to do specifically to get it to work with Zazo, specifically to get it work with one system, versus how much was work that was generalizable to any system that would be used for unlearning?
So to do the unlearning, we need to convert it to summation form. For example, take like landscape, for example, we need to get its normalized cosine similarity and convert it to summation form. And then we actually introduce additional layer, summation layer, and we modify the landscape. And the line of code actually, I need to look at the paper, I forgot the number, it's very less. I think it's just like less than like 2% of the line of code, like 0.2% of the line of code needs to be modified.
Cool, thank you. Let's thank the speaker one more time.